In today's lesson, we will discuss derivatives and rates of change, using a specific example that relates to distance and velocity. Our problem reads, if a rock is thrown upward on the planet Mars with a velocity of 10 meters per second, its height in meters after t seconds is given by h equals 10t minus 1.86 t squared. There are three questions regarding this situation. First, find the velocity of the rock when t equals a. Second, when will the rock hit the surface? And third, what will the velocity be when the rock hits the surface? Now, most people would consider velocity as a measure of speed of something in a given direction. We will be more specific and say that velocity is the instantaneous rate of change of the position of an object. We know that a derivative is the instantaneous rate of change of y with respect to x when x equals a, and thus the formula for a derivative is appropriate to calculate velocity when given a position function. So using the combination of the formula for the derivative and the formula for height given to us by our problem, we will create a formula that will provide us the velocity of the rock at any time when t equals a, which is our first question. Starting with the formula of a derivative, we then adjust it so that it reflects our height formula. Notice that the first part of this equation is similar to 10t minus 1.86 t squared from our height function, except that instead of t, we have a plus h in the first part and a in the second part. So first we distribute the 10 to the a plus h, which gives us 10a plus 10h, and we square the a plus h, which gives us a squared plus 2ah plus h squared. We notice that 10a cancels out, as does the 1.86 a squared. This leaves us with 10h minus 1.86 times 2ah plus h squared over h. Each of these terms has a common h, thus we can divide through by h to get rid of the fraction, leaving us with 10 minus 2a times 1.86 minus 1.86h. This limit has h going to 0, thus this last term goes to 0 as well, leaving us with 10 minus a times 3.72. So the answer to our question of the velocity of the rock when t equals a is 10 minus a times 3.72 meters per second, since this is a measure of velocity. Part B of our problem asks us how long it will take the rock to hit the surface. Notice that we don't need the derivative or any calculus to calculate this, as our original equation of h equals 10t minus 1.86 t squared relates distance with time. When the rock hits the surface, its height will be 0 since it's on the ground. Thus, we set the equation equal to 0. Again, at this point, it's algebra. We can cancel out a t to leave us with 10 minus 1.86 t equals 0. We can then move the 1.86 t to the other side and divide it by 1.86 to isolate the t, giving us t equals 10 divided by 1.86, or t equals 5.4. Thus, the answer to our second question is that it will take 5.4 seconds for the rock to hit the surface. Now, our last question asks us, with what velocity will the rock hit the surface? Well, from our first question, we know that the equation for velocity given a time t equals a is 10 minus a times 3.72. We also know that when the rock hits the floor, 5.4 seconds have elapsed. Thus, we calculate the velocity when the rock hits the surface by plugging in 5.4 for a, giving us 10 minus 5.4 times 3.72, which is equivalent to negative 10.088. It is negative, which makes sense because our rock is falling back towards the ground, and we originally were measuring height above the ground as a positive number. Thus, the rock hits the surface with a velocity of 10.088 meters per second. The key for understanding position and velocity problems is remembering that velocity is a derivative of position, so being provided a formula for height will also allow us to calculate the velocity at any given time.